Hello, everyone, and welcome. I'm Allan Jude, your host for today's session. Whether you're attending live or watching the recording, we appreciate your time. For those of you who are new to Clara, we're a team of open source experts helping companies design, build, and scale appliances using FreeBSD and ARM. From networking devices to industrial controllers and storage platforms, we work with teams to develop products and product-grade systems built for longevity and control. Today, we're going to talk about how to build secure, sovereign appliances using FreeBSD and ARM, how to reduce reliance on proprietary platforms, and the long-term product strategy for embedded and edge systems. Now we'll get back to our webinar. Today's session is Secure, Sovereign, and Open Source, ARM and BSD for Modern Appliances. And we're going to talk about how BSD and ARM enable secure and sovereign embedded appliances, why open source is the key to long-term independence, and some real-world applications for BSD and networking, industrial, and edge appliances, and best practices for building, scaling, and making future-proof embedded systems. We'll be answering questions submitted through the registration form, but feel free to submit them via the Zoom Q&A as well, and we'll be monitoring that in the chat. Joining us today are George Neville-Neil and Andy Wafaa, so I'm going to pass it to them to do introductions. Over to George.
If I'll go first. Hi, I'm George Neville-Neil. I am a long-term FreeBSD developer and in fact worked a bit on BSD way back in the old days. I also spent quite a bit of time working on embedded systems. I spent 6 years at Wind River doing VxWorks, which is a embedded RTOS, which runs in many places, but most famously on Mars on the Pathfinder. My background is pretty much operating systems, networking, and security.
Hi, I'm Andy Wafaa. I'm a Senior Director and Fellow at ARM. I head up our open source office, as well as represent ARM on a number of industry bodies, projects, and boards.
Great. So getting into our first topic, we're going to talk specifically about BSD and ARM and how that enables secure, sovereign embedded systems. So first, George, you want to talk a little bit about the advantages of BSD specifically when it comes to licensing for embedded in appliances?
Sure. The BSD license is a permissive license for those people who look at licensing, and that's meant that not only in Clara, but in many other places, the BSDs have been frequently used to do appliances because in an appliance, one of the things you don't want to have is people being able to extract your proprietary information or your proprietary knowledge from the lower levels of the system. The BSD license has been around for quite a long time and has gone through a few changes, but the latest version, the 2-clause BSD license, pretty much says don't sue us, which is really what we care about as a project, as the FreeBSD project, is that you consume our code. We love people to consume our code, but that we give it to you without any warranty.
Yeah, the clauses of the license are basically, don't claim you wrote this, and if you don't mind, leave this copyright notice in the documentation somewhere. And that's about the only requirement. Contrasting with the GPL, especially the V3, which is over 100 pages of legalese, and was specifically designed with the term anti-TiVoization, which is we don't want our code used in appliances. And that's the opposite of what you want when you're building an appliance. So one of the other advantages of BSD is being able to kind of pick and choose from the components and only building what you need. It's because the less code you ship in your appliance, the less code that can go wrong. You want to talk a bit about that, George?
Sure. I mean, we like to call it choose your own adventure. So in other embedded operating systems or Unix-like operating systems, it can be more difficult to remove features you're not interested in. Drivers are always easy to remove because they're meant to be removed. But in the BSDs, you can pick file systems. You can pick various network stack options. You can really customize the kernel. And in an embedded application, a lot of what people are doing, especially for an appliance, is figuring out how to configure the kernels for the appliance specifically. Being able to remove code means you're removing attack surface. So it improves the security of the system overall by not having 10 million lines of code sitting around that, maybe is leaving some port or something open that someone else can attack.
Yeah, and just the fact that FreeBSD was built with this, master options file where you can just pick and choose which features you want means that when you're building an appliance, you can get it smaller and lighter and down to just what you need with a couple of options rather than having to do a bunch of surgery to remove features you don't need and try to maintain that as a patch. And that's going to keep changing over time and causing you problems. But speaking of features that you can remove, there are also features that you can take advantage of. You want to talk a bit more about the specific security features in FreeBSD?
I mean, I can. There's quite a number. It really depends on where you're looking. So in the file system, you have things like mandatory access control. For network protocols, we support all of IPsec and the security protocols for talking to the system. We also have Andy Wafaa on, who's from ARM. So one of the things we should talk about a little bit in the future is sort of the future of ARM's security features that are provided in FreeBSD. If you look at sort of the new research system from Cherry, which I hope we'll get into later.
This next bullet point, I think.
Oh, there you go. As security features go, that's a whole secure platform.
Yeah, but like you mentioned, the mandatory access control, which is basically a way to allow you to customize all of the access control in FreeBSD with these loadable modules. And so, for example, one of the ones that Clara built for a customer is the ability to restrict the debugger that's built into FreeBSD. So when a system panics and encounters a problem and crashes, normally you have the option of being dropped into a debugger to figure out what went wrong. The problem with that is that debugger has access to all of the memory of the system, which might include private keys for VPN sessions or secret keys for encryption and so on. And you don't want that. And so we built a Mac module that actually restricts which commands you can do in the debugger to still allow the debugger to be shipped in the production version of the appliance so the customer can extract backtraces and enough information to debug what went wrong in the field, while at the same time not being able to open just any arbitrary memory address and extract information they weren't supposed to have. And then, yes, as George just alluded to, there's also the Cherry. You want to talk a little bit about what that is?
So Cherry is a new take on an old idea. So capability systems, if you look back to the 1970s, were different computer architectures built such that what we traditionally consider a pointer wasn't really a pointer. It was basically a nonce, a thing that you could use to get a hold of parts of memory. Cherry takes those ideas and modernizes them for Unix. And then Cherry itself is the set of hardware extensions to the instruction set architecture. So if you think about the ARM v8 instruction set architecture, which is what modern A-class ARM chips use, Cherry is the set of extensions to that that provides capabilities. And so in a capability system, you can't do things like just take a pointer and index off of it, which is one of the sources of, I think it's something like 70% of all zero-day bugs are basically pointer manipulation, buffer overflows, all those kinds of things that people are used to doing in C. A Cherry system won't let you do that. Capability system won't let you do that. And Cherry is available in a research architecture from ARM called the Morello.
Andy, do you want to talk a little bit about that before we move on?
Yeah, so the Cherry platform, and Morello in our case, which introduces the hardware capabilities, for us, it is one side of a double-sided coin. So we've got the hardware piece for capability, and then having that hardware on its own without the suitable software is somewhat pointless. So pairing the Cherry Morello platform with software that you control from a memory safety perspective. So, for the software that you don't own, don't control, Cherry and Morello platform will take care of encapsulating that. for the software that you create, etc., there are recommendations to write it in various memory safe languages, whether it be Rust or whatever, right? And so the two of those combined provide that fortress of compute for you.
Yeah, I think that's an important point that maybe we glossed over with Cherry, is that you can run existing software and basically add the security of pointer authentication basically to it without having to modify the software really. So like George, I think there's examples of Cherry running, a full normal desktop system and going on YouTube with a browser and so on, and not needing to rewrite the browser, but still getting all the safety as if you had rewritten the browser in a memory safe language.
So yeah, one of the things you get with Cherry BSD, which is what we call the derivative of FreeBSD that's built for pure capability mode on Cherry, also runs with all of the applications. Most applications don't need porting, although the one thing, if people are interested in capability systems that do, is generally when someone builds their own memory allocator. And of course, most language runtimes, think about Python. We now have a version of Python that runs on Cherry. But if you think about Python and Java and these other things that have memory allocators within them, those usually need to be updated to really take advantage of Cherry and to work correctly. Whereas any random C object will run on a Cherry system just like it ran on a regular system. But it will have a protection fault if someone has done something wrong. And it's, our belief that fail stop is a lot better than not failing when you have, a hidden buffer overflow or a pointer exception.
And we have looked at the whole Morello platform, and we've actually started to integrate some of the feature set that Morello and Cherry platform provided into our current architecture. It's not quite the same, but it does enhance the security capability of the ARM platform over, without having those systems. So, Morello and Cherry are a great platform for identifying areas of security enhancements that could be integrated and backported into existing architectures.
Yep. So Umit from the audience has a question asking, does FreeBSD provide kernel locking where the entire kernel runtime environment is checked against hash signatures to make sure the kernel and the code in the runtime environment are not modified? So yes, in FreeBSD, there's a set of tools around veryexec. So if you use something like secure boot to load a verified version of the FreeBSD loader, it can then extend that chain of trust by verifying the kernel before it loads and runs it. Again, using, as you said, a manifest a signed manifest of checksums. And then once the kernel loads, it can do the same thing, only loading modules that are verified, and even extend that into only running executables that are on the list of verified executables. Can even extend that to the point of only letting applications load shared libraries that are on that trusted list. So that you can ensure basically all the software running on your appliance is the software you provided and hasn't been maliciously modified or otherwise changed. So yeah, you can get that complete end-to-end security, starting with the root of trust at secure boot and extending it all the way to even the Java modules you're loading into a running application.
I think, Alan, you want to point out briefly that you mentioned modules, but what we're really talking about is kernel modules. So it's bootloader, kernel modules, and then on up.
Yeah, and so with the Mac enforcement side, the kernel can then not allow you to open a file that's not on the trusted list, even in user space. So you can actually stop a Java application from loading an additional jar that isn't on the list. It requires a little bit of modification to the software, but the open system call in FreeBSD has an extra flag, verify, and it won't let you open any file that's not on the verified list. So moving on a little bit to talk about ARM. So Andy, you wanted to talk to us a little bit about digital equality and the kind of choice and solving for monocultures by choosing something other than Linux when building an appliance.
Right, and I mean, ARM is an IP company, for those that aren't aware. So what does that mean? We create processor designs, whether it be CPU, NPU, GPU, etc. And so we come up with these designs, and we then license those to other vendors, whether it be Samsung, whether it be NXP, ST Ericsson, etc. They all take our IP, and then they implement it. They add certain features, certain functionality. Some of our partners actually add their own microarchitecture and tweak it in that sense. And so we don't necessarily build anything, but what we do have is a large collection of partners that do build ARM-based platforms, and whether it be for a microcontroller or for a cloud-based system, right? AWS is a big ARM partner. They've got their own silicon. Actually, all three of the major hyperscalers build their own silicon and run their own ARM platforms. And so we have this wide variety of hardware that people can access. And we want to ensure that we have a wide variety of software that people can leverage and create the platform that suits them best. And so for us, ensuring that not only do we have what people would expect with Linux, we have a wide plethora of different Linux distributions available on ARM. We want to ensure that not everyone wants to use Linux. Linux doesn't necessarily fit all use cases. And so working with the FreeBSD Foundation, we've ensured that FreeBSD is there as a near equal to Linux from a feature and functionality set. Not quite, but we started FreeBSD probably a number of years behind starting with Linux on supporting the ARM v8 architecture, which was our first 64-bit architecture set. And so we're getting there quite rapidly from a feature parity set. And so it enables you to pick the right tool for the right job, right? You don't have to shoehorn something and square peg round hole kind of scenario. There are features and functionalities of FreeBSD that are fantastic to leverage, and in some cases are a much better choice than running on Linux or Windows for that matter. So it's a matter of making sure that we can do all of that. The aspect of ARM's heritage comes from the mobile space, and the reason for that is low power consumption, minimal cooling requirements, etc. And so when you take that and put it into an appliance type device, if you talk about cell tower base station or something along those lines, you have a constrained footprint. It's remote, may have limited power capabilities, etc. And so you can leverage our expertise in that low power, high density for the same footprint of a single socket, quad core processor. You could probably get at least 60 odd cores on an ARM-based platform in the same thermal envelope. And when I say thermal envelope, compared to more legacy architectures, that thermal envelope on ARM includes the whole system, because ARM-based systems are systems on chips. So that includes networking, storage, etc. The whole lot is combined into that one thermal envelope. Other architectures, the thermal envelope that they publish is just for the CPU. You then have to add on what the network is drawing, what the storage is drawing, and so on and so forth. And so when you compare the two, the density and capability that you have in a single system on chip is far greater than the alternatives. And whilst we may not be the most powerful, generally speaking, most processors are running a minimum of 20% idle, if not 60% idle on a highly utilized system. And so you don't actually need all of that power. It's somewhat of a fallacy that you need all that power. There are certain cases where you do, but not for all. And so when you're looking at edge-based platforms, whether it be, if you look at automotive as an edge architecture, automotive is becoming more and more of a data center on wheels. And when I say data center, I'm talking about data centers from maybe 20 years ago kind of thing, right? But still, the amount of compute that goes into a vehicle nowadays is phenomenal. And so you need as much compute power with as little consumption as possible, especially in the day and age of electrification with vehicles and such like. There's only so much power that you can actually draw on to power the various features and functionality.
So now getting into open source and how it's kind of the key to having long-term independence and not being, saddled by any particular vendor. So George, you want to talk a little bit about why open source, or how open source kind of relieves you of relying on any particular vendor?
Sure. I mean, it's on the tin, right? It's open. So, as long as you can reach the internet, you can reach the code and you can reach the project. Now, of course, it's important to work with projects that are well-staffed, long-lived. Both Linux and BSD have been around for a long time, since I had hair, it turns out. And because of that, you have sort of like this full history of a full historical view. If you look at the FreeBSD repo, you can go all the way back to 1993. It also means there's a community of people who can help you fix your problems. And it's a very developer to developer experience, right? So it's not like there's a customer service number you call and say, oh, I can't seem to get my widget working with my thing. We still use mailing lists. People join mailing lists and they ask questions and they get answers. There's the FreeBSD forums. Open source is a community effort, a global community effort, where anyone can participate and where everyone does. So this means you don't have to, for instance, talk to customer support in Redmond, Washington, when you need to fix something in your operating system, or in your application or in your appliance. And appliances are very much tied to a thin layer of application on a thick layer of operating system and device drivers.
Yeah, and having being open source means you have full access to the source code, and so you can customize and modify it to fit your requirements. And it means, when something goes wrong, worst case, you can fix it. And, maybe the better case is that there are other people trying to use this software in similar ways to you, and you can collaborate and come up with a better solution than either of you would have come up with on your own. But just knowing that you're not going to be locked out of the source code by a vendor, or have limited access to what you're allowed to modify, or if you're allowed to see the code at all, and so on. Whereas with open source, you have access to everything. So no matter what happens, you have all the pieces to continue to build your appliance, and you don't get locked out of anything. And it also means that you can verify the integrity of the code that you're getting, right? If you're being able to rapidly iterate on your builds because you're using open source software, and if you're following the best practices that we'll talk about in a few minutes, then it means that you can rapidly iterate and verify that the binaries you're producing came from the source code that you fed into it, and make sure that you're getting all of the expected bits and nothing else. Whereas if you're shipping a binary from a vendor, you have no idea what's inside of it. Was when you have all the source code, you can build it yourself and make sure that you're getting exactly what you built, and not any surprises in addition to that.
So let me comment briefly on the reproducible builds, because there's another component to that. So until about a decade, maybe 15 years ago, while you could get all of the source code and you could rebuild it at will, a lot of source code, including the BSDs and the Linuxes and many of the libraries they use, the software itself wasn't organized in a way that was lent itself to easy reproducible builds. And that was an effort that the FreeBSD Foundation and the FreeBSD project and various other open source projects undertook about 10 or 15 years ago, because it makes it easier to localize and control for eventual bugs. This is brought about in response to a fairly famous security, zero-day security issue, in which many people realized, oh, we don't have a way of really being able to guarantee that version 1 and version 1.1, that the only thing that's changed is this one thing. So reproducible builds isn't just access to the source, it's actually a way of building software and a way of managing software, such that, currently we're on FreeBSD 15 we're coming up on, that 15 and 15.1, that you can really tell what the differences are between the two versions. Because while we did architect the system such that that should be possible, there were definitely changes made to improve that over the last decade and a half.
Yeah, and some of those are just things like don't embed the name of the computer that compiled this into the binary, and don't put the date and time it was done in there. We're going to always use this date and time as the date of the release, so that when you build, 15.0 again later to compare it to 15.1, that both of them, you don't have a bunch of spurious changes that are just the dates when they were built and things where someone might be able to slip something in. And obviously, the other advantage of being involved in open source is that when you are working on an effort to expand a certain feature or bring in a functionality, you can get community involvement and get, the amplifying effect of multiple different people collaborating and working on something rather than doing it yourself. But also maybe, George, you could talk a bit about the applicability of research, how by building something based on open source, it's more likely that academic research is going to be based on source code that's available to work on rather than private, proprietary software.
Sure. I mean, so currently, I didn't mention this in the intro, but I'm a PhD student at Yale University. So we use FreeBSD in our research. We've used FreeBSD at the University of Cambridge, where Cherry was done for over 20 years of research. And BSD comes from research, right? BSD was created by the Computer Systems Research Group at UC Berkeley a million years ago, it feels like. And one of the keys, I think, with open source that people don't really appreciate is that open source also follows the scientific method, right? So in the scientific method, you have to be able to build a thing and give it to someone else, and the person you give it to should be able to reproduce your result. Well, in open source, we're doing the same thing, right? I give you I give you a release of FreeBSD, and you can decide to verify that what I've said about the change that I've made is possible. And in fact, when the operating system developers are working on the operating system, we're constantly pulling in everybody else's changes so that we will see if there's a problem. Like if I add a bug, Allan might see it, or if Allan does a performance improvement, I can verify it. And so that works really well for research groups, because a research group, especially now, let's see, how long has the artifact stuff been around? So many conferences, ACM and other conferences, Association for Computing Machinery, now request, and I, for one, have been trying to require, that researchers produce artifacts, right? So generally, for like a major research publication, you produce a paper and some graphs. And if you're really lucky, someone produced some code and they can point you at a tag in a GitHub or some other repo and say, well, we did our performance analysis, which is what systems research people do, based on this tag. So in terms of how you do research, open source works really well for that, because we can literally give you the object. I mean, if you think about when people had to reproduce Faraday's, electrical experiments, they had to go build a rig, right? Like they had to build the same rig that Faraday built to verify the experiment, show that it was true. But in software, we can just hand you the software so long as you have the right hardware to run it on. And so open source works really well for that. It's actually an effort that we've been talking about open source for open science, which is not really part of our webinar, but it's something that people can look up.
And Andy, ARM's been making some specific investments in open source. Do you want to talk about them?
Yeah, I mean, again, this goes back to our digital diversity kind of goal. And so, as I mentioned, we invested and contributed funds to the foundation to help chair and drive the enablement of FreeBSD on ARM64. And we consistently participate with the foundation on how to further those efforts. And not only that, we've seen FreeBSD come leaps and bounds, and actually we have teams internally leveraging FreeBSD from a research perspective. And so we now have, for a number of years, we've been relying on externals, the foundation, etc., to do work in BSD on ARM. We now have a growing team internally that are working directly upstream, ensuring that FreeBSD is as good as it can be on the ARM architecture, and working closely with the existing developers that have done the bulk of the work historically, and providing guidance, help, and taking on some of the trickier tasks that knowledge and expertise lend to being able to resolve.
Can you talk a little?
I think lost your audio there briefly, Alan, but yeah, I mean, so one of the reasons why some of our research teams actually enjoy using FreeBSD is the flat structure of the project. So what I mean by flat structure is, if we look at FreeBSD in comparison to Linux as an example, Linux has this very hierarchical layout for being able to get patches into the Linux kernel. You've got the subsystem maintainer, and then that then goes up to up the food chain to Greg, up to Linus, etc. Whereas FreeBSD is you prove yourself competent and capable, and you can eventually get commit access, and so you can actually provide code contributions back to FreeBSD much quicker. Should you break something, it's your responsibility to fix it. And you have to work with those that go, hang on a second, you've broken stuff for me. It may not be your area of expertise, but it was your patch that broke it. So the onus is on you to fix it. And that makes for much more competent contributions back to the project. People don't want to, anger a whole raft of people on the internet. And so they make sure that their code is clean, they test it properly, etc., and it goes through. Yes, there is a patch review process kind of, that goes hand in hand, but that doesn't catch all cases. There's always something that kind of sneaks through somehow. But the advantage is you won't necessarily get shouted if you do break something. The developer community within FreeBSD is a very warm and welcoming part, which makes some of our engineers quite happy, because some of them start off as junior engineers and they're very scared, etc. Builds their confidence up, and actually we now have a number of them that are driving large chunks of code contributions backwards and forwards, and helping out others, and being able to mentor others in working with the FreeBSD community. And the advantage of that flat structure is it means it's much quicker to get code out the door and into products. For us, it means we can prototype new architectures far quicker. We can actually bring up a complete operating system from desktop all the way down. We can validate everything. If something doesn't work, okay, let's go and work with it, fix it, get the patch in. Does that actually work how we expect it? yes, no, whatever, and then we can iterate and keep going that way. Whereas working on other operating systems, it can be far, far slower. Code, coming up with an idea, getting the code down, submitting the code for merging can take, getting it merged, it can take you anywhere from 6 weeks to 16, 18 months in Linux, right? It just depends on where in the kernel it lands. On FreeBSD, it's far, far, it's a matter of weeks. And so that time to market is accelerated astronomically.
Yeah, like you said, if you submit something to the development branch of FreeBSD, once that's merged, people start using it almost right away. Within weeks, it's running on, a subset of all Netflix boxes around the world, and then, in less than 6 months, it's included in the next release. Whereas Linux, like you said, it can take 18 months to convince some lieutenants to let you merge it, or to merge it on your behalf. And then it's in mainline Linux now, but when's a distro actually going to ship a version of that kernel that actually includes your work in something that your customers can run? And so it can really take the time to market from, it can be weeks or months in BSD, and it can be years on the Linux side.
Well, and since we're talking about appliances, the key here is actually reducing technical debt, right? So if I've got a fix and it's unrelated to my proprietary bits, and I put that up into FreeBSD, it's going to appear almost immediately in the development branch. If I'm tracking the development branch, my technical debt is zero. If I'm tracking a minor release branch, my technical debt might last for a few months. But for people who build significant embedded systems or appliances, things where a lot of code has changed, one of the keys to longevity and to maintenance is just making it so that we're not maintaining, a 10,000 or 100,000 lines of diff that we need to keep private until we can actually do the upgrade. And everybody has, I don't know about everybody, but certainly Alan and I have been through, large upgrades where you're like, oh, I wish we had put this in sooner. And FreeBSD's more flat, open, shorter round trip structure makes it so that it's up to you. You could get that stuff in as long as your company is happy with that, and you're a committer. It's probably not going to be that much of a problem, especially if it's bugs in a driver you're working on or bugs in some small component you're working on. That stuff can get in almost immediately, and then you don't have to maintain it. It's part of the project.
Yeah, and we'll get to talk a lot more about that in a minute when we get into best practices. But let's quickly take a tour through some of the real-world applications where people might not know about, FreeBSD and ARM together already being used in appliances. So yeah, FreeBSD is used in a lot of appliances, especially in the storage space, where almost all the large storage vendors have a version of their product that's on FreeBSD. And then in networking, FreeBSD has always had a long history in the firewall, VPN, and related industries, and especially devices that are monitoring traffic, looking for just overall metrics and being able to do packet inspection and figure out what's going on with the network, and even just providing analytics to what is popular on the internet. Most of those appliances trying to digest a raw feed of the internet use FreeBSD's network stack because it is so long-lived and well-trusted.
And also, by the way, clean. So it's not just networking devices, but if you look at, so I come from the embedded systems world. If you look at a lot of the current open source and even closed source embedded operating systems, if you look back to VxWorks, which is still maintained,
QNX
because
and lots of other ones,
and FreeRTOS, all of those used the stack because the work that Sam Leffler had done in the original stack, and then the Stevens books describing it, describe a really coherent design that hasn't been ripped up and redone repeatedly. And that is one of the things. So I'm a networking person. I really care about this part. That is one of the things that has really made FreeBSD a system that's used in networking, because the system is clean, has clear boundaries, tractable, well documented.
Yeah, and that even leads to when we start looking outside of the operating system and looking at user space networking, things like libuinet that provide a networking stack in user space is extracting the FreeBSD's networking stack and putting it into an application so that you can reuse it even inside other operating systems. And obviously, if you're going to do that, you're going to pick the best one. And the one, like you said, that's the most maintainable and the easiest to understand and work with. And because of that, it's generally the one that's going to give you the best performance because you can understand why it is working the way it is. And then, Andy, you had mentioned specifically, ARM in the data center, both in public cloud and private cloud and images and so on. And that's an entire genre of appliances is basically building these cloud appliance images where you can go in the Amazon marketplace and get a specific application and basically run that in the cloud as an appliance.
Yeah, absolutely. It's where we've seen a huge uptick in adoption in the cloud space.
And a lot where, for example, at Amazon, using ARM-based instances is less dollars per hour than legacy architectures, right?
Yeah, that's correct. By default, if you go for an EC2 image, or if you go even on Azure or Google Cloud Platform, by default you'll get an ARM-based instance because it's cheaper, it's lower power drain for the actual data center as a whole, and it just makes sense, and so it fits good 95% of the workloads, and so unless you are specific with your requirements, you need a legacy architecture for a particular reason. You'll need to stipulate that when you spool up your instance, and it's going to cost you more.
So as promised, getting into a bit of best practices. Kind of as George was talking about, one of the best practices if you're going to build an appliance on FreeBSD is what we call upstream first. So if you're going to develop a feature that is not your core IP, you want to develop that feature with the intention of upstreaming it to the FreeBSD project. And if you design it where you're going to upstream it and get it reviewed and merged into FreeBSD before you ship it in your appliance, that provides this forcing function to make sure you don't write something that's just good enough, or you're not cutting corners, where it's going to come back and cost you more later. So if you design knowing that other people are going to see this and are going to have comments on it, then you tend to build in something that you realize you're going to have to maintain this, and other people are going to have to believe that you're going to maintain this, and so you build something that is going to pass scrutiny there. And the advantage of that, once you do that, is that the maintenance of that is collective, right? The reason why they're not going to let you just throw something unmaintainable there is because it's not only you that's responsible for maintaining it. It's now part of the global code base, and every additional commit somebody else makes, if it disturbs that, it's their fault for breaking something that was working. And so it means that later when you go to update to the next version of FreeBSD in your appliance, that code's already been maintained and already works in the new version. Whereas if you had kept it internal, then you're responsible for rebasing it and dealing with all the things that might break because you didn't upstream it. Whereas once it's upstream, if somebody else breaks it, that's their fault. But if you keep it internally, when they do something that breaks it, they have no way of knowing because you didn't upstream your bit. And so now it's all on you to maintain it. And that just accumulates that technical debt. And the longer you let it go, the worse it gets. So George, one of the ones you wanted to talk about was just following the development methodology of the upstream project that you're working with.
Sure. I mean, I'll talk pretty much mostly about FreeBSD since the methodology I know best. So we don't have our usual fancy graph of current and stable and all that. So I won't wave my hands to describe it. But one of the keys to development on FreeBSD is knowing on which branch which things can happen. And that all starts from a thing we call POLA, the principle of least astonishment, which means when you make a change, changes that would surprise another developer. I mean, our consumers are developers and not generally, you know, someone, a home user. But when you add a new feature, or you change an API, or you update a driver, or any of these things that you would do in an operating system, you have to do that with an eye towards what we call POLA. And that means that you can make a lot of different types of changes in the head of the tree in what we call current. But once something has been made stable, so let's talk about an older version of FreeBSD. If I'm in version 14, if I have made a change to an API, say I've added a new argument, or I've removed an argument, or I've added a new system call, that API or system call or meaning of what is going on, that must be maintained throughout the entire branch. So that means 14.1, 14.2, 14.3. We don't make changes to the programmer visible, let's call it that, parts of the system within a major release, because that would violate POLA. So it's really, there's only a couple of rules there. People will, some people, and I believe Netflix still does this. Some companies will really track the head of the tree, and they will try to stay right up to date with the head of the tree, which is admirable. Requires a bit more work because we can have surprising changes in that. Other companies will pick a release branch to follow and then decide when they're going to move to the next numbered up release branch. Generally, when I've consulted on this and discussed this with people, you don't want to go too far down the branch, especially if you're in an area where the hardware is changing. So, generally when you build an appliance, you're like, oh, we're targeting this particular board or this particular ARM design or what have you. But at some point, 1, 2, 3 years down the road, there's going to be a higher performance version. There's going to be a lower power version. There's going to be a version with some maybe crypto offload feature you want, something like that. Hardware changes under you. And so you have to plan for how you're going to move between the major versions of the OS. But having these commitments, long-term commitments to API stability across major revisions is actually extremely powerful. And it's very interesting. I won't mention the open source project, and it's not Linux, but another open source project. A group of developers had come to a FreeBSD developer summit, and we had described the development methodology. And there's this one slide that all of us have seen a million times. They're like, well, here's stable, and here's where we branch. Here's how we do minor releases, blah, blah, blah. And we talk about the stability of APIs. And one of the developers caught up with me at lunch and said, "Oh, that's so nice." And I said, "What do you mean?" It's, "Oh, on the internal of our like multi-million line project, multi-million line project. Internally, we don't have to have API stability." And I was like, "But that seems," he said, "Yes, it's very difficult." So that fairly simple methodology is what we follow. And it's documented. It's in, I believe, the FreeBSD Developers Handbook, which is online. So one of the nice things on FreeBSD is we have a tremendous amount of documentation that's well maintained and is public. So when people want to start a company building on FreeBSD, there are actually really a small number of places to look. There's the Developers Handbook, there's the Committer's Handbook, and then there's the FreeBSD General Handbook. There are some actual books about the operating system, one of which I co-authored. But those will give you not only like, what does the code do, but how do we develop the code? And so that's really useful. I see.
Understanding the way the bits are put together and just where things belong and why they're that way really helps you.
Yeah.
If you follow that same thing in your downstream, it means that much easier when you're upstreaming, but also just when you're trying to ingest more changes from upstream, like you said, moving from 14 to 15 at some point, you'll understand where the pieces are coming from, what was allowed to change, what isn't, and you'll really understand where breakage could be and how to resolve it, rather than if you kind of try and go and do your own thing, every time you try to resync, you're going to have this impedance mismatch.
And one other thing on that, which is um, the workflow for FreeBSD, because it's an operating systems workflow. And, applications, languages, operating systems, databases, each of these sort of large corpuses of software, they have they can have different workflows. For people building appliances, which is kind of what we're talking about today, appliance workflows and operating system workflows are not that different, because of the fact that generally building an appliance has always meant picking an operating system and then maintaining it, or maintaining the ability to integrate with it. So I always think it's great, and I always recommend this when someone says, "Oh, we're going to build a new widget, whatever, and we'd love to use FreeBSD." If you can convince them, which I try to do, to follow a similar workflow development methodology to the one we use on the operating system, it's just going to be easier. We've got the tooling in place. We've got the processes, which are really a lot of it. I know programmers don't like to talk about process, but we've got the processes in place that if you adopt them, at least the operating system part should be fairly straightforward and relatively easy to maintain and update.
Yeah, and moving on to the next point, like Andy was talking about earlier with ARMS standing up a FreeBSD team, being an active part of the community and just talking with the other developers and contributing code lends weight to your voice, so that when you are trying to get a feature upstream, that there are people willing to review it, because you're not just a random person on the internet who showed up one day. You're somebody that's been nurturing this connection to the community for a while, and also allows you to participate in things like the FreeBSD Vendor Summit, where we talk about things that we are planning to do ahead of time, and that helps you find synergy with other people that are working on this, and just slotting that into the plan and have an idea of what is going to change in FreeBSD over the next year or two. And that can really help you drive your own planning and make sure that we cut off any surprises, or find out, if there's going to be a conflicting change from someone else, how can we reconcile that ahead of time, instead of after people have invested a lot of money in development and then have to try to kind of redo it to solve the conflict.
Actually, go ahead, Andy, sorry.
Sorry, John. Yeah, just one quick one on the participating in open source. There are a number of ways that you can actually participate in open source. It doesn't just have to be ones and zeros, right?
Mm-hmm.
There's all sorts of different areas. If you're artistic, if you have a marketing slant, if you are good with documentation, there are a million and one ways to participate in open source. And if you're not sure how to participate, but you want to participate, just ask. You'll be inundated with suggestions as to how you can get stuck in. So don't let that put you off.
For sure.
And I was going to pile on the vendor summit bit, especially for companies that are building projects with FreeBSD. One of the things that's great about participating in one of these summits is it's not just about finding out what's going on, but also we have a session we called Have, Need, Want, which is vendors will say, well, I have this piece of code and it's something I'd like to upstream, but we haven't had time, or we need someone to look at it, or something like that. But then there's also, we need a certain feature to do a release, and wants are kind of like, well, it'd be really great if we had this thing. But that's usually about a 90-minute session in which the entire, sort of community, or at least especially the community of vendors, can come together to sort of express what they want out of the future of FreeBSD.
Yeah, and basically by being an active participant in the community and having that voice, you get to help steer where this goes. And that's, something you often don't get if you're, getting your operating system from a vendor or just, silently consuming an open source project without being part of the community. Yeah, and our last best practice is just making sure you're using modern tooling and following the kind of current best practice for the upstream project. So if you're building the release for your appliance, you want to be doing that the way the upstream project builds their release, because they're going to keep that one working because that's the one they use. And so, if you end up on an orphaned system or rolling your own release system, you're going to have to adapt to every change upstream makes. But if you can work with the tooling they provide, then you can build these things much more quickly and take advantage of, for example, if you want to build a cloud appliance off FreeBSD, if you use FreeBSD's image building tool, it can automatically integrate all the bits to, keep it working. And the people that maintain FreeBSD on GCP and Azure and AWS are constantly improving that and adding the bits so that it will work with the newest instance types and so on, and you won't have to maintain all of that yourself. Okay, so to wrap up, since we're quickly running out of time, you can maintain sovereignty over your device and your IP by avoiding software lock-in from a specific vendor, by having control of the open source, and by upstreaming the bits that aren't your IP, you reduce your maintenance burden. And with the BSD license, you get to keep your core IP to yourself and don't have to fold yourself into loops trying to comply with the GPL. You can enhance security by avoiding monocultures, having optional components, and not choosing the same software that everybody else does. Making sure that you have the ability to switch stacks if you need. Would Heartbleed have been the same thing if we actually had more than one SSL library back in the day? And that to truly be using open source, you have to be participating. As Andy said, it doesn't have to be giving back code, but you have to be part of that community and actually actively involved. Otherwise, you're just consuming and not actually participating in open source. All right. Thank you both for joining us. That was great.
Thanks for having me.
So that completes our session. Thanks everybody for joining, and I hope you found this insightful. If you have any follow-up questions or want to learn more about Clara, feel free to reach out to us. I have a couple of QR codes on the screen right now to our specific services around FreeBSD and ARM. Be sure to keep an eye on our webinar page and our social media channels, as we will be having another event next month. And we try to regularly host these webinars on key topics and challenges, and we'd love to see you all again.